Right. Hi, everybody. Welcome to our last high energy phenomena seminar of the semester. Thank you all for joining us all through the semester and of course today. And thank you very much to our speaker for joining us. We have a special 1 hour long talk today and that, excuse me, excuse my cough, please. We have a special 1 hour long talk today from Dr. Lia Corrales. She received her PhD from Columbia University, where she was a NASA Earth and Space Science Fellow working with Dr. Fritz Perls on dust scattering halos in the interstellar and intergalactic medium. After that, she took a postdoc position with the Chandra Hetchi group at MIT, working on software tools and developing techniques for extracting the Chandra high resolution X-ray spectrum from Sagittarius star. She received an Einstein Fellowship in 2016, which she then took to the University of Wisconsin-Madison to work on dust scattering echoes. And now she is a faculty member at the University of Michigan. She's a leader within the Prism science team and is translating her expert on the interstellar medium to study exoplanet transmission spectroscopy at short wavelengths. So please, Leah, take it away.
Thanks for that introduction. I appreciate it. And I'm really excited to talk to you all about some interesting science and some new science that is just recent for my research group. So I'll jump right in because I know we're limited on time. So as a new faculty member, I felt like I needed to find a cohesive name to describe all of the different types of research topics that we do. So I settled on SPICES, which stands for Space Particulates in Complex Environments, because it's really partly the glue that brings all of these topics together. So we work on a variety of things, including astromineralogy, exoplanets, and the Galactic Center. And I have an incoming graduate student that will be working on the Galactic Center science, which you might know me for a little bit with the Sagittarius star spectrum. So I will leave that to them for a future talk because they will be taking over that science. So the last two topics represent what I'll be talking about today. In the first part, I'm going to talk about astromineralogy in the interstellar medium. And the postdoc in my group is Iona Tsareraki. And she's doing excellent work. And so I'm really excited to showcase some of the stuff she's going to be working on as well. Okay, just a quick note on the dust life cycle and how we think about dust in the interstellar medium. As we know, a lot of heavy metals in the universe are produced via nuclear synthesis, and then they are disseminated out into interstellar space through stellar evolution and death. We know that a lot of dust is produced in AGB stars and core collapse supernovae, although it's not clear how much of that survives because of processing in the ISM, mainly by shocks that are within those supernovae themselves, as well as sputtering in hot gas and by cosmic rays. But at some point, those interstellar metals and that dust makes its way into molecular clouds where it's efficient at growing, and it also aids in chemical processes in those clouds. Eventually, those materials make their way into star formation, and they are processed in disks where they can dissolve and then reform into particles that make up planets. And then this whole process starts again. So despite having a really nice graphic to tie this all together, there are actually quite a lot of uncertainties along all of these steps in the process. So some of the big dust questions that I've identified for myself that I find particularly interesting is understanding how dust changes phase in the ISM, how does it survive in the ISM, and asking ourselves whether supernovae are a net source of destruction or creation for dust, because there's a lot of weird controversy around that. One thing that I also find particularly interesting is how dust influences the physics of the ISM, in particular, perhaps feedback processes in the ISM. So this nice image in the background is M82, which has these really famous galactic outflows, which you see in the hot gas component in blue comes from the X-ray image, and the red component is from Spitzer's. So you can see that there's some dust intermixed in these outflows to some degree. And finally, dust affects nearly every type of astrophysical observation, including things like the cosmic microwave background, and people can use that to measure interesting properties of the ISM. But all of this comes down to also understanding the microphysics of the dust processes that are producing, either radiation or some sort of extinction feature that we use to infer properties of the ISM. So this background image is a polarization map of the nearby Orion cloud. Yeah, Orion molecular cloud. And this is supposed to represent the magnetic field lines as well as the abundance of dust in this region. So I'd like to argue that answers to these types of questions are all found in understanding the grain sizes and mineralogy of dust in different environments of the ISM. So why should we study dust with X-rays to begin with? I like to show this plot. It's a very broad picture overview of how dust in the interstellar medium extincts light across the entire electromagnetic spectrum, from the X-ray all the way to the infrared. Of course, in the far infrared, in mid-infrared, we're actually seeing more emission from dust. So we're not always probing things like these features. But it's well known that dust is really good at extincting optical and UV light. So people tend to look through dust by going to the near infrared. But then on the flip side, X-rays are also, or the ISM is just as optically thin to extinction in the X-ray as it is in these near infrared bands. And so this really gives us an opportunity to probe a very large column density of the ISM, usually between 10 to the 20 and 10 to the 22 or 10 to the 23 in the X-ray, and get at a lot of those properties of dust that are really kind of the microphysical properties. And another point I'd like to make is that the X-ray band covers photoabsorption from all of the major interstellar metals: carbon, nitrogen, oxygen, iron, neon, all these. So these are the most abundant interstellar metals. And what happens is that in the X-ray band, you're able to see transitions from inner shell electrons. So n equals 1 K shell electrons or n equals 2 L shell electrons. And you get, when you get to photons around that energy range of the photoelectric potential for that particular electron, you see a big jump in the absorption cross section. And the strength of this jump depends on both the abundance and, of course, the strength of the transition in those particular elements. So this is one way that we can look at nearly all of the major metals in the ISM. And the great thing is, when you go to high resolution X-ray spectroscopy, you can start separating out the gas and solid phase components. So on the left, this is one of the first observations of Cygnus X2 with Chandra LETG. And you can see that they see an atomic line, but then they also see some residuals which they attribute to a compound. So that was like one of the earliest attempts at looking at solid phase material with X-ray spectra. We now have much more advanced models, and I'll get back to the oxygen K shell features. But this is an example of how, if you take just pure silicate grains, and this is just a model oxygen K shell feature, we have better ones for this now. But you can see that when you add on to that some of the gas phase absorption, there's plenty of features that kind of pop out separately. So this black line is the combination of the gas and the solid phase component for just test oxygen K photoabsorption region. So in the X-ray, we basically use galactic X-ray binaries in the same way that people studying like the IGM or the CGM would use background quasars. So these are really bright X-ray point sources that, due to the fact of stellar evolution, are mostly in the plane of our galaxy. This plot here shows plenty of targets that are available in the Chandra archive, and here I've overlaid them on dust emission map, the EB-V map, which shows you like where these things are relative to the dust in the Milky Way. So there's plenty of dust to probe with these targets. This figure up here shows how many more targets are available when we get a new telescope that has at least 10 times the effective area of Chandra, which is pretty easy to do at this point, especially on the low energy side, where we're most interested, where most of the features of interest appear. So in order to do astromineralogy with X-rays, we want to look at X-ray absorption fine structure. So this image here shows the cross-section measured in the lab for several different iron hosting compounds from Julia Lee in 2009. And here in the solid line, you just see like a general theoretical cross-section that just takes the photoelectric edge into account. But there are resonant features that occur in real life on top of that. So this black dashed dotted line shows you pure metallic iron. And then these other compounds show you that there are plenty of bumps and wiggles over that original cross section that have to do with the crystalline structure and the way that atoms are bonded into the mineral. So one way to think about that is that really an X-ray absorption fine structure is like a perturbation on what you would get from the pure gas phase or the pure neutral phase of that particular atom. And this is because basically as you're exciting electrons in the atom when it's in a crystal, you can think of the probability function of the electron kind of scattering off of other electrons in the nearby atoms. So I really love this paper by Julia Lee and Ravel in 2005, where they looked at some of their compounds and they said, okay, let's look at the residuals between what we actually see, like the XAFs that we measure, and what one would expect from a pure photoelectric absorption model. And so you can get some bumps and wiggles. This is an example of what that perturbation looks like. And then you can do a Fourier transform on that, which is what this inset is. And you get peaks in the Fourier transform that tells you about the spacing between the atom of interest and other atoms in the crystal. And here's just a few other examples of that. So basically, if we, even if we can't directly identify whatever these minerals are, we do have some hope of learning about what types of structures they're in, and the sort of spacing in the compounds as well. So one of the key pieces of science that I was interested in, as Rutu mentioned, I did a lot of my thesis work on scattering. ISM dust produces arc-minute scale scattering halos in the X-ray as well, which are directly imaged with any telescope with sub-arc-minute scale resolution. And they are exceptionally sensitive to really large grains in the ISM. And by really large, I mean 0.3 to 3 micron size grains in the ISM. And so this offers us a complementary way of understanding grain size distributions in the ISM. And in particular, because we have better imaging resolution with our telescopes now, compared to some of the earliest measurements, we can actually resolve the scattering halo from the point source. And so that means when you put down a little extraction region for your spectrum, you're actually not including the scattering, which means that the scattering component has to be included into your extinction model. So the simplest way to do that is just to add the absorption and scattering. So this plot here from my 2016 paper shows what happens to the iron L edge extinction as you include the effect of scattering, which is in the dotted line. And it will also depend on the imaging resolution of your telescope. So that's what these blue lines show. These are just for example telescopes with about 5 arc second and like 10 or 15 arc second resolution. So that's what that's looking at there. And of course, as you get to larger dust grains in the ISM, the scattering component of these features is much more dramatic. And actually the absorption goes down because of shielding and the scattering dominates. So you get a completely different looking extinction edge. So there is some indication that we can actually see some of these scattering features. And basically when you take, when you take an optical depth like this and you fold it through as transmission for your power law spectrum, these little dips, which are really on the low energy side of the absorption feature, these dips in the extinction cross section cause you to actually have something that looks more like an emission feature in your real spectrum. Sorry, my cat has decided to join us. So we have some observational indications of that. Here's an observation of GX5-1 from Ziegers et al. Looking at the silicon K edge. And they were able to say, well, we think we see some sort of upturn here in the spectrum that we can attribute to a power law distribution of 0.1 to 0.5 micron grains that are mostly scattering. And then we also have a measurement by Schultz et al. Who looked at a large number of silicon K photoabsorption features. And in this particular, I believe it's also GX5-1, in this particular spectrum, there's some weird feature here that could potentially be scattering. We're not sure, it could also be instrumental, but either way, one of the things they also pointed out is that they were able to pull out a separate atomic silicon K edge and a silicate, so solid phase K edge, along with some other absorption features that we believe are intrinsic to the binary. So in order to really model these things correctly, we need the complex index of refraction because this really helps us to account for the effects of self-blanketing. It's not just adding a scattering component onto an absorption component. You kind of have to do them both at the same time. All right. So I want to talk about some high priority questions for dust in the ISM, kind of needle pointing into like some more specific questions than I mentioned earlier, and some partial answers, basically some recent work on those particular questions. So I'll focus on two in particular, that's oxygen and iron. So for oxygen in general, it's been observed that when you looked at the most depleted regions in the ISM, you would expect if all oxygen was soaked up into silicates, so that's like SiO4 or SiO3, which also takes up a lot of magnesium, then at some point you would run out of magnesium and silicon in the ISM because there's much less of it than oxygen, and the oxygen depletion should saturate. But instead, we see that oxygen smoothly continues to saturate as you go to more and more depleted phases of the ISM when we're looking at UV absorption features. So this indicates that oxygen is able to basically condense out of the ISM independent, not in a silicate form. So this is one case for potentially water ices that could form into larger composite grains, meaning that they're made out of multiple components. And this is something that in particular would be interesting to study with X-ray scattering, because again, if it's kind of creating these big mantles or growing these dust rains, then we're gonna see them more in the scattering side than the absorption side. But anyways, we'll talk about that in a second. And then also another interesting question is trying to understand how iron becomes dust, because the vast majority of interstellar iron is produced by type 1a supernovae, and there's no evidence of dust production around type 1a supernovae as compared to core collapse supernovae. So that's kind of an indication that iron enters the ISM, or the majority of iron enters the ISM in the gas phase, and so it needs to condense directly out of the ISM, and understanding the physics of that condensation process, measuring directly the mineralogy of iron in the ISM will help us understand that. So one particularly nice paper that came out recently was Westfalidal, where they did a few lab measurements of iron L shell absorption from materials that were basically taken from the Stardust mission. So like actual materials that could, that were in space. So they were able to fit the spectrum of SIGX1 with a little bit of scattering. And they looked at metals, a combination of metals, sulfides, and amorphous silicates. They didn't find any iron in the gas phase. And they basically said it's, there's no more than 40% of interstellar iron in silicates. It's probably, a combination of silicates and metals. And in particular, they were looking for sulfides, because if you took solar metallicity gas and just condensed it, you would expect about 50% of the iron to be in sulfides. And so they weren't really super able to to give support for that, although it's only, it is still within the 2 sigma contour of their particular examination. But I really like this examination because it really tries hard to put these iron absorption features into context with mineralogy that we understand, at least in our solar system. And like I said, it's interesting to try to understand how oxygen condenses in the interstellar medium. And I call this the oxygen problem in X-ray astronomy. One of the things is that, in early work, people saw residuals and they say it must be solid compounds. But then by calculating cross sections for gas phase ions, just even O2 and O3, and here you see also even, it's still just O1 and O2. There's a little bit of O6 and O7 in there. Basically, people were able to completely fit this oxygen K shell structure without any solid phase component. And so they said, we don't need solid phase, which a lot of us said, well, we know it, there's some in the solid phase, so what's going on? And this required really lab-based measurements that didn't exist until very recently. So Elisa Costantini has a group at Esron in the Netherlands where they're doing lab-based measurements of these L and K shell photoabsorption features. And Iona Tsariraki, like I mentioned, is in my research group now, was in her group working on the lab cross-sections for the oxygen K shell. So those are now published in her recent paper, and she fits those to the Cygnus X2 sightline. So there are a few things to notice here. In order to fully do this fit, it requires a multi-phase component of the ISM, which makes a lot of sense. So you have like a cold phase component that gives you the O1. You have a warmer, probably like H2 environment component that gives you some O4 and some O3 or O2 as well. And O4, O3, and then there's the O2 right here from like the middle phase component. And then the other thing is that you can see here that this amorphous olivine cross-section, at least when you fold it through with the response for XMM, you get something that's relatively featureless and smooth. It's just a bump. And that could very easily explain why people were having trouble finding residuals, because basically it's just a smooth transition. And so you can fit all of the, peaky, strong features that you want and knock it out a smooth thing. So this was a really nice piece of work. And I just want to point out that doing this mineralogy is quite intensive, because she points out in her paper that basically they had enough cross sections in order to try over 1,800 combination of fits. And really they can't narrow it down to anything better than 300 possible combinations of those. So we do really need high resolution, super high resolution spectroscopy to distinguish between some minerals. So next, what we want to do is start including multi-wavelength observations of the ISM into the context of these X-ray fits, so that we can constrain them a little better, because there is a lot of degeneracy between the different ion abundances you assume for the gas and whatever you want to assume for your dust mineral, because as I mentioned earlier, the X-AFs are really a perturbation on this gas phase cross-section. So what Iona is working on now is looking at UV absorption spectra of a few key X-ray binaries. This is an example of what the HST data looks like for SIGX1, and there's two, for example, iron 2 features that are easily visible. So we're working on kind of tying all of these things together so we can fit simultaneously and get a better constraint on the actual gas phase abundance. And as I mentioned, we do need really high resolution spectroscopy in order to fully distinguish these compounds from the gas phase. So here is a nice simulation of what Arcgis could do. Arcgis is a concept mission that would have like R of 5,000 gratings, for instance. And gratings are really key for getting at these softer energies in order to look at oxygen and carbon. Okay, so what are some future avenues for research that I'm particularly interested in? One of them is looking at these dust scattering halos and getting a spectrum out of them directly. So when you look at dust scattering halos, this is a particularly spectacular dust ring echo that arose from Circinus X1. And in this nice work by Sebastian Heinz, he was able to identify different features in this image and tie them to maps of CO or molecular clouds in the ISM at different distances. So for example, this cloud right here corresponds to this brightness right here. And that means that there's an increase in the scattering because there's an increased amount of dust. So you see a bright spot. But then this cloud, which is in the foreground, actually absorbs some of the dust scattering halo, which arose from clouds that were behind it. So we see a shadowing effect. And so you can see the shape of this cloud right here, absorbing some of the background rings. So one of my dreams is to be able to look at dust echoes like this with an X-ray IFU instrument that would get us a high resolution spectrum of the scattering halo itself. So the scattering features, as I showed earlier, have resonant structures around these K shell and L shell photoabsorption features just naturally. So you can also look at the dust scattering halo by taking its flux and then dividing it or just comparing it to the point source flux. You can actually normalize out a lot of the absorption features and just look at the scattering component. And in that particular case, you know, pretty much everything is coming just from solids, and you can get rid of a few degeneracies in interpretation. So we can imagine, you know, plopping down a spectral extraction region on some cloud or dust echo area of interest, comparing it to the point source. And then when you do that, you can get features that come out very easily to distinguish between different mineralogical components and as well as determine abundances and grain sizes. So both of these simulations are for 50 kilosecond observation of GX340 plus 1. They have slightly different resolution. This one's R of 3000 for an effective area of 1 meter squared. Here you can see it's R of 1000 versus a microcalorimeter, but in general, this is something you could do with the next generation of telescopes that use microcalorimetry that give you much better resolution than our current CCD resolution of 100 to 200 eV. So as mentioned before, I am on the Prism science team. And if you don't know already, Prism is the next generation after Hitomi. And here you can see a nice example of the spectrum of the Perseus cluster from Hitomi and how it's able to resolve these iron K alpha features compared to a CCD spectrum. And it's even good enough to do Doppler broadening, for instance. So we're quite excited for this X-ray IFU to give us better high resolution spectra of diffuse phenomena in the interstellar medium. And I also just want to advertise that the Prism PV targets have been selected. So you can go to this website to look at everything that is planned to be observed in the performance verification phase of the telescope. We're launching late 2022 to early 2023. One of those targets is GX13 plus 1. This is a simulated observation of what GX13 plus 1 would look like with the PSF of Prism, which is definitely not as good as Chandra. And some sort of expectations we have to distinguish between different mineralogies and different grain size distributions in the silicon features. So please stay tuned for a NASA call for guest scientists to join individual target teams, which should be coming out later this year. So I think I'm doing okay on time. I will pause here and ask for questions while I put up some of my main conclusions from this slide.
As usual, you can put any questions so far into the chat or raise your hand to ask them directly. We have one hand raised. Randall?
Hi, Leah. Great talk. Thanks for the shout out to Arcgis. How would you, the problem of getting the data for all of the dust components is obviously a huge and ongoing one. Do you see any way of speeding this process up, and any comments on how we're going to pick which dust analogs we should be using next?
Yeah, that's a great question. I mean, I would really love to see just more multi-wavelength studies of, including X-rays into what people already know about dust from the infrared and other perspectives. So I would say we should start looking to what people have been doing in the infrared as, what they think the most likely dust species are given their observations. Because there's definitely stuff missing from the Lee paper that I showed you. Some of those compounds aren't necessarily things that you hear about associated with the interstellar medium. And I know that Julia was interested in getting more compounds from things like the Stardust mission or things that we actually see in space. So I really like that idea. I'm guessing that you were asking more about the lab aspect of it. It is definitely a huge endeavor, it sounds like, to do the lab absorption measurements, which is one reason I've personally never tried it. But I definitely think that, I'll just kind of end with, I think more multi-wavelength choices, things that people think, for example, are in protoplanetary disks. There's lots of compounds there that I haven't necessarily seen studied from the X-ray lab perspective. But I feel like the SRON group would have more to comment about that.
All right. Any other questions at this point? Yes, Jonathan?
I was wondering if you were aware of this work by Hensley and Drain, suggesting that instead of two populations of grains, we have carbonaceous and silicates intermixed in grains. This was based on, I think, polarization in the submillimeter.
Sure. I don't think I've read that paper in particular, but I think that composite grains are definitely really interesting and something that I would like to study from an X-ray perspective. I think it's particularly interesting because the way you would treat the cross sections in the extinction would be fundamentally different from just, say, choosing one mineral and just calculating the scattering and the absorption component. So in order to do that, you really need the optical constants rather than just, a blanket absorption factor or something like that, which is mostly what gets published, although you can kind of back it out with Kramers-Kronig, which is what we're doing actually right now with some of the Lee compounds from her 2009 paper. So I would say just based on that, yes, it's kind of on my radar doing composite dust grains. And in addition to a mixture of silicates and carbonaceous grains, I'm also very interested in, there's work by Zirakovska that basically does simulations of condensing dust in situ in the ISM and suggests that iron is mostly in these really tiny nanoparticles that can then they must be embedded in silicate grains or something similar in order to survive in the ISM to get to the iron depletions that we see in the UV. So that it would be particularly interesting because you definitely, in my opinion, can't just say, oh, we'll just throw some iron in and do the me scattering and say you're done. So thank you for pointing that out.
Okay, thank you. Leah, do you want to move on to the second part? Okay.
Yeah.
So I guess I'll attempt, could you hear the timer last time?
I couldn't.
Okay, so I'll just let you watch time then.
Yeah.
Yeah, thank you. Sorry about that.
This aspect of the talk is definitely shorter. So the next thing I want to talk about is exoplanets and a project that I started with a postbac researcher, Sasikrishna Ravi, who has moved on to other things now. He's doing data science, and but are now continuing with my postdoc, George King. And I'd like to highlight some of his work as well in particular. So with my interest in ISM and particulate matter, I decided that I wanted to try my hand at looking at particulate matter and exoplanets and observing exoplanets in general from a high energy perspective. So usually when you talk to the exoplanet community about high energy stuff, the first thing that comes to mind is evaporating planets, because there's some evidence now that the high energy environment is very important in just explaining some of the populations that we're getting for exoplanets. So one of the key results there is the, it's the period radius gap. I always forget what it's called, sometimes called the Fulton gap. So an example is shown right here. So you can see that basically as you look at exoplanet populations, you can see that there's a bunch of planets that are kind of missing at short periods in particular. So as you get closer to your star, you get kind of a bimodal distribution of planets. So one of these, in this particular paper, they show that you could explain this bimodal distribution by photoevaporative mass loss induced by X-ray and UV photons, or mostly extreme UV photons from the host star. So in order to get this bimodal distribution, they look at photoevaporative mass loss model, and they show that, okay, as you decrease in orbital period, you get a lot more small planets that are rocky and Earth-like or super Earths really. And then as you go to larger orbital periods where the radiation is less intense, you can have some larger planets that probably keep a hydrogen envelope. So that's kind of some of the central motivations for understanding why we get some of the planet distributions that we get. And George King has worked a lot on understanding how to translate the X-ray properties of stars into their extreme UV components. So his 2018 paper, he looks at the flux in the EUV versus the X-ray, and does a bunch of work to come up with a slightly more precise scaling relationship between X-rays and EUV. Also in this paper, I'll show a little bit later, he also looks for UV transits of some planets. But he's also, I would just say he's an expert in understanding the X-ray and EUV evolution of planets or of stars and how they could potentially affect their planets. So in his most recent paper, he showed that basically when you look at the X-ray flux of a star, we assume this relationship that the star's activity is sort of saturated for some period of time, and then it starts to die off as the star becomes less active. But he showed that basically the EUV component to that kind of tail off in terms of activity happens slower than the X-ray. And people really focus on the X-ray saturated phase when they're doing these mass loss models because they say, well, that's when all of the flux is happening. That's when all of the mass loss is happening. But actually the majority of the mass loss isn't induced by EUV, extreme UV radiation, and that can still be quite a large effect later on in the planet's life. So even at 3 gigayear, a planet is not done evaporating its envelope. And so people just kind of assume, if it's a gigayear or so, like we don't have to worry as much about mass loss, but there's still active mass loss that could be occurring. And then when you look at transmission spectroscopy, people can look in the UV in order to get signatures of active evaporation. So one of the most famous ones is GJ436b. It was observed by Ehrenreich And they were able to look at alignment alpha feature. So this is the emission feature from the star. And you can see that in the blue side of the feature, there is quite a large dip when GJ436b transits in front of the star. So that's like a 50% dip, and it's also blue shifted. And they're able to interpret this observation in the context of a huge amount of a hydrogen escaping atmosphere with this cometary tail that's kind of spilling out behind the planet. So that's a really, really well-known and exciting result for understanding evaporative mass loss in planets. So now we're going even lower energy and looking into the NUV. So the NUV is likely to probe iron and magnesium in the exosphere and has been seen in some planets such as WASP-121b to suggest an escaping atmosphere. So in this particular observation, they look at absorption from the exoplanet's atmosphere, and they compare the strength of these iron 2 absorption and magnesium 2 features. And they say, well, all of these features are deeper or imply a larger atmosphere, because when you look at the transit depth, you're basically measuring the size of the exoplanet atmosphere, that wavelength. They're saying, well, the size of the exoplanet atmosphere in iron 2 is larger than the Roche lobe, so it must be escaping. That's one of the key things that people look for. But in addition, you can have the exosphere, which is basically the atmosphere of the part of the planet's atmosphere that is very hot and not in thermal equilibrium, and it usually spans about 1 millibar up to 10 to the minus 12 bar. And in this really nice work by Young et al., they showed that by incorporating this exosphere, they were able to get planet transits in iron 2 and magnesium 2 that are as large as 30 or 50%. And now this is for a particularly high, for X-ray standards, resolution of around 100,000. And of course, as we're looking towards slightly lower resolution or broadband transits, a lot of this stuff is going to be smoothed out. So at U of M, we have access to SWIFT, and this is a telescope that, as you know, was originally designed to study gamma ray bursts, but because it has UV capabilities, a really fast slew time, and a flexible schedule, we decided to try it out for capturing NUV transits of exoplanets. The first NUV transit with SWIFT was actually measured by Sals et al. In 2019 for WASP-121b, that planet I mentioned earlier. Just a little bit more background. This is an ultra hot Jupiter at about 2300 Kelvin with a high estimated atmospheric escape rate. And as I already showed, there are some iron 2 features there. And when they looked at the NUV transit of this particular planet, they noticed that it was 35% deeper than the optical. And that is much deeper than you would expect given some standard assumptions for atmospheric models. So if you take the optical transit or the optical radius of the planet, which is right here, and you look at the Rayleigh scattering slope, which is basically what people attribute to small particles and molecules in the upper atmosphere, that's kind of how you get an upward trend in terms of UV absorptivity in a lot of exoplanet transmission models. You can see that the actual radius that they measured was much deeper than that. So in order to explain this, they invoked iron 2 absorption. So we decided to look at as many exoplanets as possible with SWIFT. So we picked 5 exoplanet systems, and they're really just selected based on the likelihood of us being able to detect a transit. So we looked at NUV bright host stars with magnitudes around 14 to 15, and at hot Jupiters because they exhibit transit depths on the order of 1%. So I just wanted to show that we're able to reproduce the results of Sals et al. For WASP-121b. Just to explain this plot, this is the relative flux for the filter we're using on SWIFT UVOT. We measured a transit depth of about 2.25%. We also did a little bit of extra work to try to correct for instrument systematics by using a population of field stars just in the same observations and monitoring them for changes across the light curve. And we also do null hypothesis testing. So I just want to explain this plot. When we fit the transits, we assume all of the optical transit parameters, but we leave two things free. We leave the planet radius relative to the star free, that's this y-axis. And we let the transit midpoint be free, just to account for any issues in the timing calibration or unknowns in the ephemeris values. So that's what this is. This is the offset from the predicted midpoint of the transit in kiloseconds. The other thing we did is we allowed our exoplanet transit models to have this non-physical RP over R star be less than 0. And basically what that does is we say if it's less than 0, pretend that the light curve went up instead of going down. And that's just to account for any noise and systematics, so we're not forcing a transit to be measured. So when we do that, these are the results of an MCMC fit to this light curve. This is the 1 and 2 sigma contours. This plus shows the best fit. And this shows the result of null hypothesis testing where we simulate light curves with the same scatter and the same distribution of error bars. So this is basically this is a 5 sigma result. So the detection for WASP 121b is pretty strong. So the other light curves for other planets weren't all as good as WASP 121b. This is the best looking one that we got. This is XO3b. This is actually a really weird, wacky planet. It's a hot super Jupiter. So it's almost a brown dwarf, but not quite. It's about 10 Jupiter masses, and it has a highly eccentric orbit. It has a moderate temperature, and because its mass is so high, it actually has a very low estimated escape rate. However, when we look at this transit and we do our null hypothesis testing, we get about a 3 sigma result. So this is the best one that we got. But the NUV transit is 4 times the optical, meaning that the radius is about 2 times the optical. We also have a potential early transit, although the ephemeris values are relatively uncertain for this particular target. So it's 2 or 3 sigma to within uncertainty. So I just wanted to showcase this, this best example we have of another transit observed with SWIFT. This paper has been submitted, it's under review. So, please don't share these slides or anything like that. What we're seeing, so this object in particular is interesting because Sauls et al. Suggested, maybe these NUV transits are correlating with mass loss because we're looking at iron 2. But it turns out that XO3 has, like I said, the lowest estimated mass loss rate in our sample and the highest NUV radius that we found. So we said, okay, it doesn't necessarily correlate with mass loss rate. Maybe it's something besides iron 2. And, I'm biased. It could be lots of things, but I'm biased towards saying, hey, maybe it's aerosols. So in this particular plot, I'm showing the filter transmission properties for UVM2 and UVW1. These are 2 different filters on Swift UVOT that we have some results for. And I'm showing what happens when you have 1 micron silicates clouds, for instance, in the atmosphere versus a 0.1 micron silicate cloud. And basically, one of the things I would say is that we need to be cognizant of the fact that the UV is going to be really sensitive to these 0.1 or smaller clouds or cloud tops that actually do extend quite high into the atmosphere of planets, including hot Jupiters, because you can get these really enhanced extinction properties compared to the optical out here at 500 nanometers. And then something I'm also really excited about is looking at hazes as a source of UV observation. And this shows lab absorption measurements of hazes under different oxidation states in the UV band that we're probing with SWIFT. So there are lots of things to look forward to. George also just submitted a paper with the UV transit of the canonical hot Jupiter HD 189-733b, which was observed with the OM UVW2 filter, very similar to the SWIFT filters. And they have an X-ray transit coming soon. You know, HD 189 has already been observed to transit in the X-ray, but they have 20 orbits that they've looked at and are actually able to fit things like the transit through the limb brightening that you expect in the X-ray. So you get this like little double peaked transit, which is really cool. So that is also coming soon. Yeah, so I'll stop here. It's really just a taste of what we're starting to do. We're starting to look at incorporating aerosols into some transmission spectroscopy tools that are used in exoplanet observations, and trying to put together some toy models to try to explain some of the results that we're getting from SWIFT, as well as continuing to get more transits with SWIFT as time goes on, so we can build up a database of NUV transits, as well as follow up with HST. So there's more to come. Happy to take questions now.
All right, let's thank Professor Corrales for a great talk. If you have any questions, please raise your hand in the participant window or type it into the chat and I'll read it off. All right, we have a question from Scott Wolk.
Hi, Leah, great talk. Obviously, I'm really interested in the second part of what you were talking about. We had obviously done some work on HU 189-733 earlier. I hadn't thought about looking at it with the SWIFT UV, but it looked like your data, the noise in the data was a lot bigger than one would have expected just when you're staring, even at the COM bend there, when you're not looking at a dip. Is that just the telescope would need to be larger, or is there something intrinsic in the orbit that keeps the background really high?
I really don't know. One of the things that we had to account for was like telescope jitter. And when we were looking at the observations in event mode, the pointing was not very stable to within like a few arc seconds. So there was a lot of work to like slice up the data, like recenter the extraction aperture, and then, do that over and over again, as well as aligning, because you have like multiple image files within one event mode observation, and you have to kind of like stack them all together to get the time bin that you want. So I would actually guess that it has more to do with like jitter on the pixels themselves.
It's just
Yeah.
Pixel variation or something like that.
Yeah, that's my best guess.
I'm trying to see a transit there when I take the line away. And I think if I go to the back of my office here, I might be able to see it once it gets blurry enough.
I definitely agree. Yeah. What I would say is that it's really just like following the average of each of these transits. And of course, this is not like a chi-squared-of-1 type of fit, which is why I was really concerned about like convincing myself that this could actually be real by doing the null hypothesis testing. So this was the only thing that convinced me that these results were somewhat publishable. But I would say I'm really interested in finding, for instance, a grad student to work on hammering down these systematics a lot more. And, people have tried, it was a lot of work to try to get Spitzer to do exoplanet studies because of things like this. So we could look at things like pixel level decorrelation, or even looking intensely at getting into some of the more systematics. Like I was also thinking like maybe gain fluctuations or temperature fluctuations and things like that.
All right, well, I look forward to the next season of this to see if it all stays the same. Looks really good.
Yeah, me too.
All right, we have another question from John Raymond.
Hi. When you look at sun grazing comets near the sun, all of the dust evaporates when it gets into about 11 solar radii, and the temperature rises to maybe 1500 degrees. So you're mentioning higher temperatures than that. Are these especially refractive compounds that you're thinking about for the haze?
So I showed some hazes. We actually don't expect hazes to dominate hot Jupiters until they're like less than 1000 Kelvin in terms of equilibrium temperatures. So for the hot Jupiters I showed, hazes are not likely what's absorbing or what's in the atmosphere. The consensus right now is that hot Jupiters 1200 Kelvin to 2200 Kelvin. So like WASP 121, for instance, is an ultra hot Jupiter and is not likely to have aerosols. But the regular hot Jupiters are believed to have silicate clouds. And those silicates can actually grow quite big. There's also plenty of high temperature refractories that can form in hot Jupiters as well. I'm thinking right now of just a paper that shows that silicates are the dominant absorption structures in hot Jupiters, especially when it comes to the near infrared. But yeah, so it's definitely not like volatile ices like you would see in comets for the most part.
Any more questions? If not, then let's thank Professor Corrales for a great talk once again. And thank you all for attending and attending our last seminar for the academic year. And we will keep you updated as to what things will look like in the fall.
Yeah, thank you very much, everyone. I appreciated the questions and discussion.